Very good. So it's 4:10, and so it's 4:10. I just like to get the colloquium started. So it's my pleasure today to introduce my colleague and friend Kent Moore from the University of Toronto, Mississauga, part of our physics department. A long-serving member also of the life and at the University of Toronto, Mississauga. So Kent's areas of research in this field of Earth, atmosphere, and planetary physics is focused on the geophysical fluid dynamics of the atmosphere and the area of polar climate in particular. So he's done a lot of work on what's called mesoscale meteorology, the dynamics of storm systems that are a few hundred kilometers and get very intense in Arctic regions, polar meteorology in both Arctic and Antarctic regions. He's done a lot of work in the field, really important experiments off the coast of Greenland, off the Beaufort Sea, and Arctic, the other parts of the Canadian Arctic, for Labrador Sea as well. And his interests are really in that coupling between the ocean and the atmosphere, which is such an important part of what controls weather and climate on a whole range of timescales. And so he's highly published, has a very, very productive research career here. And he's also served in administrative capacities. So those of you from Mississauga will know him as the vice principal research there. And he is, I think that's a continuing appointment. And he's currently on sabbatical or just about to start a sabbatical leave. And previously, he was the Fulbright chair at the University of Washington on a sabbatical in, I believe it was 2017. So he's a really important part of the Arctic community here, and I'm looking forward to hearing about his thoughts on our amazing Nobel Prize in this area of research and his own work focused on the behavior of Arctic sea ice in a changing climate in Canada's north. So Kent, please go ahead, and I will be on the lookout for any questions as they arise.
Well, thanks, Paul, and thanks for this opportunity. So today I want to talk about two things. One is about half of the colloquium talking about the Nobel Prize in Physics this year, especially Suki Manabe, who was one of my professors when I was in graduate school. And then I would like to talk about these really interesting features that develop along Nares Strait. We'll talk about where Nares Strait is in a minute. But essentially, it's between Ellesmere Island and Greenland. This is an image from June 2020. This is all sea ice here. And then there's this feature we call an ice arch, which is probably about 100 kilometers long. And then downstream of the ice arch, there's open water. This is Plenia, an area of open water in the Arctic known as the North Water, and it's the most productive Plenia in the Arctic. And what's really cool with these arches is they'll remain stable for upwards of 6 months. So from December typically through to June, a feature like this will just be rock solid there. Ice will form downstream in the winter, and of course, be blown downstream by the winds. But this arch really doesn't change for upwards of 6 months. So they're really, really quite remarkable features. I won't have time to talk about another little Plenia over here. And this one actually is, there's a region called Flagler Bay. And it turns out that there's evidence that the Inuit and the pre-Inuit cultures actually used this Plenia upwards of the last 4,000 years as a place that they were able to hunt. And of course, the thing about a Plenia is that it's a region of open water. It's like an oasis in the desert. And so this area of open water here, which is built for at least 4,000 years, we think, was used during that whole period of time for hunting. So there's a really rich, actually, history in this area as well. Unfortunately, we won't be able to talk about this feature today. So again, as we all know, the Nobel Prize this year was awarded to 3 scientists who work sort of on complex systems. 2 of them were geophysicists, Suki Manabe and Klaus Hasselmann, who have done work on modeling the Earth's climate. And Manabe, it's been reported that when he was called at whatever 5 in the morning, or whatever, told he had won it, he said, "But I'm just a climatologist." And I think most of us in the climate science community had exactly the same kind of thought. When I got up that morning, my wife told me that some climate scientist from Princeton, who maybe you knew, had won a Nobel Prize in physics. And I said, "That's impossible." because geophysicists don't win Nobel Prizes. So again, I think it was a really, really important prize and a really well-deserved prize. I think not only, for the work that Manabe and Hasselmann have done, but also just, I think it's another recognition of really the important and pressing global issue we have to deal with, which is the warming climate. And so I was fortunate enough to have Manabe as a professor. And so what I want to talk about today is his contributions to climate science, and then also my own research into these ice arches. So to start, we got to kind of do a little bit of sort of basic physics. And the kind of most important parameter in the climate system is the surface temperature of the Earth. And so how can we predict the surface temperature of the Earth? And so the basic idea is that the Earth is in thermal equilibrium. There's some radiation coming in from the sun. Some of that is reflected right back to space by clouds or by sea ice. The Earth is emitting radiation as well, and thermal balance says we should have a balance between all these three terms. Now, in the climate science community, we often use a shorthand we call shortwave radiation, solar radiation. We talk about long-wave radiation, which is really the terrestrial radiation. So if we assume that the Earth is in thermal equilibrium, can we in fact predict the surface temperature? There's a little bit of geometry we have to deal with. The solar constant, this essentially is the radiation coming in from the sun, and it's about 1,340 watts per square meter. There's a little bit of geometry we have to deal with. So for instance, the Earth is absorbing that solar radiation in its cross-sectional area, but of course it's radiating energy to space, the total area. So there's a factor of 4 pi that kicks in between these two. We have to deal with the fact that the Earth is reflecting some of that radiation right back to space. That's what we call the albedo, and it's about 0.3. And so if you do that, you have this rather simple model. We have incoming solar radiation. We have outgoing long-wave radiation. Assuming the Earth is a black body, of course, the outgoing long-wave radiation is a function of the ground temperature to the 4th power. And if we solve this, what we find is we predict the surface temperature to be about 255 Kelvin, or minus 18 degrees Celsius. And of course, this is way too cold. If in fact the Earth was this temperature, we wouldn't be here because of course our biology requires water in its liquid form. So what are we missing? The atmosphere. And this comes to a very interesting sort of history of how we've studied the interaction of radiation with the atmosphere. Eunice Foote, who was an American scientist in the 1850s, she did some very interesting experiments with these. Essentially, this is a recreation. These glass vials. She put a thermometer inside them. She filled some of them with carbon dioxide, some of them with just in a vacuum, and studied essentially how they cooled down after they'd been exposed to solar radiation. And she was able to. She actually, of course, it's a really sad story. Of course, being a woman in the 1850s, she had no standing in the community. She had this paper. She wasn't able to present it. Someone else had to present it. And what's probably even sadder, of course, is that her work was forgotten about for almost 150 years. But with this experiment, she came up with this, again, incredibly prescient comment. This is a direct quote from the paper. An atmosphere of that gas would give to our Earth a high temperature. If at one point in its history, the air had mixed with a large proportion than at present, an increased temperature must have necessarily resulted. So with this experiment, Eunice essentially had grasped the basic idea of the greenhouse effect. Carbon dioxide and water vapor in the atmosphere warm the planet up. Around the same time, John Tindall, who was an Irish physicist working at the Royal Society in London, essentially came up to the same conclusion. Now, he had a much more complicated setup. I was at a meeting for the centenary of his death a few years ago, and they actually they had reconstructed this rather Harry Potter-ish looking device. But essentially, he had a heat source over here. He had a pipe that he could put gases in here. He actually had a null sort of a null sample over here, and so by doing this, he could essentially assess whether or not gases in this pipe were absorbing infrared radiation. And what he found is that water vapor and carbon dioxide did absorb, and oxygen and nitrogen didn't. So again, exactly the same thing that Eunice had, and he concluded that if water vapor and carbon dioxide were not in the atmosphere, then the Earth would be held fast in the iron grip of frost. So he again had come up with this idea that the Earth is, the warmth of the Earth is in part due to the fact that we have these gases in the atmosphere, which are absorbing long wave or infrared radiation. So how can we do this? Well, a very simple model, just following on the one I had before, is we just now include an atmosphere in the model. This atmosphere, of course, will have some temperature, so it'll be radiating both to space and towards the surface of the Earth. We're now going to essentially characterize the interaction of this atmosphere with both long wave and short wave radiation by two parameters. There's a short wave transmittance here. So F naught, this is the solar radiation coming in, only a fraction of it gets through to the surface. Of course, the rest is absorbed by the atmosphere. And then a long wave transmittance here. We have a certain amount of radiation, long wave radiation leaving the surface, and only a fraction of that gets through to the space, and the rest is absorbed by the atmosphere. It turns out that for the most part, the atmosphere is transparent to shortwave radiation. So we can assume that the shortwave transmittance is about 1, means 100% transmittance. The long wave transmittance, again, this gets a bit fudgy, but we can estimate it's about 0.2. So about 20% of the radiation gets through to space, the other 80% is absorbed. And so now you actually have to solve for two temperatures. You need to solve for the temperature of the atmosphere and the temperature of the Earth, but it turns out to be just two linear equations and two unknowns. And you can solve that. And when you solve it, you find out that T sub G in the presence of the atmosphere is now about 280 degrees Kelvin, or about 15 degrees Celsius. So we get essentially what we would expect for the average surface temperature of the Earth. And so the important thing here then is that the Earth's warmth is really the result of the atmosphere's greenhouse effect. And now we hear a lot in the news about global warming and greenhouse effects. And of course, what you have to distinguish between two greenhouse effects. There's the natural one, which is due to the natural levels of CO2 and water vapor in the atmosphere. And that's a good thing because that warms the planet up. And of course, then there's the, if you like, the anthropogenic or the human-induced greenhouse effect, which is the result of the added CO2 and also water vapor that is being put up into the atmosphere. And that's, if you like, the bad greenhouse effect. So this model is pretty good. Gets us the right answer, but of course the devil is in the details. And there are a number of problems. There's more than this, but these at least are three of them. First of all, the atmosphere is not a single layer. It's clearly, has some continuous temperature profile. So having a single T sub A is a little bit of a problem. The other thing, of course, is it's not easy to relate this long wave transmittance to the concentration of greenhouse gases. One can do that if you go back to first principles and look at how gases interact, how radiation interacts with the gases in the atmosphere, but it's not easy to relate this transmittance. And the other problem, of course, is if I say, well, if we double CO2, how does this factor change? And we don't really know. It's obviously going to become smaller, but how much smaller? We don't really know. The other problem is, and this is a big issue sort of in the climate system, is that there's a positive feedback that exists here. And that is, if you have a higher atmospheric temperature, that means the atmosphere can hold more water vapor. And of course, water vapor is also a greenhouse gas. And that would lead then to a smaller transmittance, okay? And so it's not clear how you would account for this positive feedback. In the climate system, there are also negative feedback loops. For instance, if you put more water vapor in the atmosphere, you have more clouds, and clouds actually reflect solar radiation to space, and that would tend to cool the planet down. So in the climate system, we have to deal with these positive and negative feedbacks. And of course, depending which one wins, has a big impact on what the outcome is. And so often we have incomplete knowledge on these feedbacks. And so when you have positive and negative feedbacks, you may be having an error because one may be too active, one may be not active enough. And so people starting, I think Eunice was the first person to try to estimate this parameter that we call the climate sensitivity parameter, which is the increase in surface temperature that happens if you double CO2. He came up with a value of about 6 degrees Celsius. He was trying to estimate this positive feedback loop, and that's why he got such a large number. But there's a whole host of papers written from 1900 to about 1950 where people tried to essentially quantify the sort of if you like, the results that Tindall and Foote had, that CO2 and carbon dioxide warmed the planet up. And if you read these papers today, they're really kind of frustrating to read. There's a sense that people were struggling. I like to think of they were struggling in the dark. They had a flashlight. They were trying to see what was in the room, and clearly they were having a very good idea. And so the papers were all over the place. Some people got a value of 10 for the climate sensitivity parameter. Some people got a value of 2. So there really was no sort of consensus. And what Manabe really did was he just turned the light on. So he, as we'll see in a minute, he had a totally different approach to estimating this S parameter. It turned out to be by accident and doing something else. And he really turned the light on. And once you turn the light on, you see what's in the room and you kind of see what's actually going on. But before we sort of talk about what Manabe did, we had to digress a little bit, because it turns out that Manabe's work was essentially came out of pioneering work in numerical weather prediction, which started after the Second World War. And it actually was John von Neumann, who had a real interest in turbulent fluid flow. Computers were available after the Second World War. And so he led a project at the Institute for Advanced Study in Princeton to produce weather forecasts. Again, he was really good, and he recruited probably the leading meteorologist at the time, Joel Charney, to lead this effort. This is a picture. So ENIAC is the first computer. It's in the background here. These are some of the people involved. Of course, I always like to look at these old pictures and realize how the sartorial splendor of scientists has gone down over the years, right? We don't wear suits and ties anymore, but these are essentially a bunch of the people involved. This is John von Neumann here. This is actually a scientist from Norway, Ragnar Fjørtoft, who did some really pioneering work in this area. And this is Joel Charney here. And this is the paper that they published in TELUS, which was the first, if you like, numerical weather forecast. People had tried to do this before. There was a very famous failure about 20 years earlier than this by a guy called Richardson, who attempted by hand to integrate the Navier-Stokes equations. In one day, he got a pressure change of about 100 millibars, and typically the pressure change from day to day, maybe a few millibars. And so this was a colossal failure. It failed for a lot of reasons. One reason was he was trying to integrate these very complex set of equations, which included things like sound waves, and he wasn't filtering the sound waves out. And so we think what happened is the sound waves just quickly, due to a numerical instability, amplified to very, very high values. And so what Charney had done a lot of work on essentially looking at balance flow in the atmosphere. So of course, the atmosphere, one thing that makes the atmosphere interesting is it's a rotating environment. And on this sphere, there's a very strong constraint on fluid flow given by the fact that the Earth is rotating. And so Charney did some very pioneering work in that area. And essentially they used this technique. They did not try to solve, if you like, the Navier-Stokes equations. They solved what's called the barotropic vorticity equation, which is an equation which assumes that flow on the Earth's surface is in some sort of balance. And it turns out this is a much more efficient way if one doesn't have a large computer to do these sorts of integrations. Now, the first time they tried this for a few times, it took about 24 hours to do a 24-hour forecast. So clearly there's not much value in that because the atmosphere is doing it in the same time it takes you to do it. But that's just a technical problem. The problem was the computers weren't very powerful. Within a couple of years, John von Neumann built a special computer at the Institute for Advanced Studies, and the runtime was down to about 5 minutes. So clearly this is now quite doable. And of course, what you want to do when you get the runtime down to 5 minutes is you want to make the model more complicated, so you include more physics in it. And so this is always the kind of pressure, if you like, that happens with numerical weather prediction and also climate models, is that you never have a big enough computer. You always have to make approximations. And then when you get a bigger computer, you can relax some of those approximations. Today, if you ran this same model on a laptop, it would take a few milliseconds to do. So again, just showing you the incredible increase in computing power in just, in a lifetime. It's pretty quite remarkable. So eventually, this project spun out of the IAS, and it became an arm of the US Weather Bureau. It was called the Geophysical Fluid Dynamics Laboratory. And under the leadership of its first director, Joe Smagorinsky, GFDL really was the preeminent center for climate research during the 60s to the 80s. And it did really pioneering work on a bunch of things, weather prediction, data assimilation, coupled ocean atmosphere models. What happened over time, of course, is that, you know, the climate is such an important issue, weather prediction such an important problem, that other essentially institutes spun up. Some of them actually were sort of spawned out of GFDL. And so now, of course, in the 1960s, there may have been one climate model on the whole Earth was being run at GFDL. Now there's 50 or 60 of them. And so part of the sort of, if you like, decline in relative importance of GFDL is just because there's many, many more players now than there were back in the 1960s. So Smagorinsky was a really, he was a top-notch scientist. He'd done some really kind of groundbreaking work on numerical weather prediction, but he also was a really savvy manager. He also saw the value of university government collaborations. So in 1968, GFDL moved to Princeton University. The graduate student folklore that was passed down from one class to the next was another reason for this move. And that was that Smagorinsky, whatever level he was in the US bureaucracy, was not entitled to a private washroom. And by moving to Princeton University, the Princeton University owned the building, and so he was able to have a personal washroom. So that was the story that the graduate students told. I think the real story was that Smagorinsky really saw the value. Once he was at Princeton, he could attract graduate students. You know, there was people at the university he could work with, and also, of course, postdocs and things. So it really was a quite important move. The building's really quite a nice building. This is it here, was built in the 1960s. My office was there when I was there. And GFDL really always prided itself on really, really fast computers. In fact, they were the fastest computers in the world for a lot of its existence. And when I arrived there my first fall, one day I arrived and there were a whole bunch of groundskeepers looked like picking acorns up off of the grounds. And I asked one of my friends who'd been there a bit longer what they were doing. And it turns out that every fall, the squirrels, there's a large squirrel population in Princeton, one of them would chew into the power conduit feeding the computers. And the computers would, of course, crash. There's a big problem if you cut the power on your laptop today. But if you have a room full of iron, which is hot, and you turn the power off, it has problems. It always took them a couple of days to restart the computer once the squirrels had chewed into the power conduit. And so these groundskeepers were trying to keep the squirrels away by picking up all the acorns. Of course, the squirrels were fried, as well as frying the computer. And again, so Smagorinsky was a really sort of creative individual. And he saw that this technology that had been developed for numerical weather prediction had other uses. One of them was just the study of the general circulation of the atmosphere. So could you in fact understand, why the winds are the way they are, why the temperatures are the way they are, why the precipitation is the way they are? And this is called the general circulation of the atmosphere. And of course, there's a related problem. That is, can you understand the future evolution of the climate system when you change greenhouse gases? And so Smagorinsky really saw the value in essentially going beyond just NWP. And again, I think he's one of the first people to realize this. And he could use the same technology to study things like climate change. He also was a really skilled administrator, and much of the success that GFDL achieved, I think, was a result of his skills. Suki Manabe once told me that Smagorinsky went to every meeting with his superiors with his resignation letter in hand. And if they didn't give him what he wanted, he would threaten to resign. And given his stature, they probably caved most of the time. And of course, one of Smagorinsky made a number of really incredible hires. Of course, one of them was he hired Suki Manabe. This is a picture of Manabe and Joe Smagorinsky in 1972. If you look carefully here, you can see that they're looking at a really interesting problem. So the top panel here is essentially a general circulation model. That is a model that's being run to essentially, if you like, calculate the state of the atmosphere. And this is the precipitation field if you run that model with mountains present. And you can see this is precipitation along the equator called the ITCZ. You can see there's some precipitation here up along the western coast of North America, or this is, of course, due to the topography of the Rockies. This is the same model run without mountains. And if you look carefully, you can see there's no longer much precipitation along the essentially west coast of North America. So you can, and of course, this is the observations. There's lots of problems with sort of reconciling this model with observations, but at least you can see there's this large region of precipitation along the equator. And so, to first order, they're actually getting that right. And so these are the sorts of things that Manabe and Smagorinsky did. In fact, the reason why I was attracted to doing graduate work at GFDL was when I was a senior, I read a Scientific American's article on GFDL, and they mentioned they did these sorts of experiments where they took the mountains off of the Earth and they saw what happened to the climate. Thought to be a pretty cool thing to do, given that we actually can't remove the mountains. And so this is actually what attracted me to the field when I was an undergraduate. So when Manabe first arrived at GFDL, Smagorinsky got on working on essentially parameterizing. That's the word we use for representing the interaction of radiation and the atmosphere. Again, Smagorinsky had this idea of building these climate models. And of course, to do that, you'd have to be able to parameterize how radiation interacts with the atmosphere. Computers at the time, of course, this was the 1960s. They were really, really underpowered in the 50s. They were still underpowered. And so it was a real challenge to test these parameterizations. And so what Manabe did with a longtime collaborator, Dick Weatherall, they developed a one-dimensional model that was able to predict the vertical temperature profile of the atmosphere under the influence of two processes: convection, as we'll talk about in a minute. This essentially is a process where heat is being transferred up from the surface, and also radiative processes in the atmosphere. Of course, a 1D model, is an order of several, maybe many orders of magnitude faster to run than a full climate model. And so they were able to very quickly sort of, if you like, with this model, assess things. And it turns out that one of the consequences of this model was they were able to essentially understand the impact that greenhouse gases have on the atmosphere. And this is probably the simplest model, if you like, that does this in a realistic way. And this really was the one of the things that Manabe did that garnered the Nobel Prize. As scientists, I think we are not very good at naming our titling our papers, and this is a rather obscure title for a paper. But if you look at the last paragraph in the abstract, you can see that this is a really important paper. So he says, according to our estimate, a doubling the CO2 content in the atmosphere has the effect of raising the temperature of the atmosphere when there's a fixed humidity by about 2 degrees Celsius. Our model does not have the extreme sensitivity. This is the problem that people had before. Their predictions were extremely sensitive to the model. And so their model did not have this sensitivity. This paper has been called the most influential climate science paper. So this is not the figure from the paper because it's pretty much unreadable in the paper, but this essentially is the main result that they have in the model. So this is altitude and this is temperature. And so what you can see that this is called the troposphere, the bottom, let's say 10 kilometers of the atmosphere, the temperature decreases with height in the troposphere. And that's because, again, the solar radiation is being absorbed at the surface and essentially the troposphere is heated from below. And so the temperature drops off at some rate, and anyone who's climbed a mountain sort of knows it gets colder as you go higher up. But once you get up into the stratosphere, you see that the temperature now increases with height. And that's because in the stratosphere, we're actually being warmed in situ, mostly by ozone. They did these 3 runs here. They did a run where they had 150 parts per million, which is about half, if you like, the pre-industrial level of CO2, which is about 300, and then they doubled CO2. If you look down here carefully, you can see that as you increase the CO2 concentration, the temperature at the surface increases. In the stratosphere, the opposite thing happens. In the stratosphere, as you increase CO2, in fact, actually the temperature is cooler. So this is a fingerprint, if you like, of global warming, is that if you increase CO2, you warm the surface and you cool the stratosphere. This is the table from the paper that essentially won Manabe the Nobel Prize. And so you can see over here, they have an estimate of this S parameter. If you have a fixed relative humidity, that is, you allow essentially the relative humidity is always constant. As you warm the planet up, there's more water vapor present because, of course, you can hold more water vapor in the atmosphere. And essentially, this table argues that this S parameter should be about 2. So if you double CO2, you increase the surface temperature by about 2 degrees Celsius. If you look at observations, this is temperature data, annual surface temperature data. This is CO2 data. And if you essentially do essentially a logarithmic fit to temperature and CO2, you come up with a value for observations, which is very close to what Manabe got, 2.2 or so. This is a table showing the estimate of this parameter as a function of IPCC report. The first IPCC report was in 1990. The last one was in 2021. And this shows essentially the uncertainty of this S parameter as a function of time. And what you can see is that, again, the value of S is somewhere around 3, maybe from, to say, 2 to 4. And of course, Manabe's estimate, again, this is run on a very simple 1D model in 1967, is within the uncertainty range of the most modern and the most complex climate models we have today. Manabe did other things as well. He also finally achieved Smagorinsky's vision of using what are called the primitive equations to generate a realistic global climate model. This is work that was published in 1980 with Manabe and, again, one of his collaborators, Ron Stouffer. This is an interesting paper. I want to focus on this. They quadrupled CO2. So again, we typically talk about this climate sensitivity parameter S, which is if you double CO2. Why were they quadrupling CO2? And the story goes is that back in 1980s, they were still using punch cards. Ron Stouffer was given the job of setting up this run. He punched a card that said CO2 equals 2 times CO2. And the humidity of a Princeton summer caused essentially 2 copies of this punch card to be created. He ran the deck. It probably took them 6 months or so to run the model. And at the end, they saw the results were a little bit, they were much warmer than they thought. Suki asked Ron to go back and check the deck. And in fact, he had actually quadrupled CO2. So again, these are sort of heroic first calculations. They didn't want to spend another 6 months running the model with a double CO2, so they ran it with a quadruple CO2. So this is essentially just, again, an evidence of really how heroic some of these first calculations were. This is the result that they got. Again, this is a rather idealistic view of the Earth. This is the Northern Hemisphere, the Southern Hemisphere. This is the annual increase in temperature. This is the winter, and this is the summer. What I want to focus on is that the warmest increase, the largest increases in temperatures occur in the wintertime in the Northern Hemisphere. And we now call this Arctic amplification. And so again, in addition to all the other things that Manabe was able to sort of do in his work, he was essentially one of the first people to recognize that the warming that we're seeing is amplified at high northern latitudes. This is the result of some positive feedback loops, type I mentioned before, that amplify the changes at high northern latitudes, only in the Northern Hemisphere. You also got a result in the Southern Hemisphere, but this is probably an artifact. And if you look at a modern climate model, this again is a GFDL climate model. Again, you see exactly the same thing, this enhanced warming at high northern latitudes during the winter. Given this is a US product, this is in Fahrenheit, so don't get too stressed out by 20. It's 20 degrees Fahrenheit. It's still quite warm, but it's not 20 degrees Celsius. Anyway, so that's essentially an overview of Manabe's contributions. Now I'd like to spend the remaining time talking about the work I do on ice arches in Nares Strait. So Nares Strait is this strait between Ellesmere Island and Greenland. It's about 500 kilometers long. It's about 40 to 100 kilometers wide. It's got very steep topography on either side. And so it's a very challenging area to model in just because it's such a long, narrow strait. It's also really important because it's a conduit by which ice from the Arctic can flow southwards into Baffin Bay and eventually into the North Atlantic. And so this is a article written on some research that I've done in it. And this is a plug, if you like. We'll talk about it. The arches that form along Nares Strait act as a plug. They keep this ice from moving southwards. And there's an idea this plug might be becoming leaky, and that'll lead to a loss of ice out of the Arctic. So this is a video that I want to run. This is a synthetic aperture radar animation. Again, this is Nares Strait. This is Lincoln Sea. This is Nares Strait. If you look carefully, it's a really high resolution. SAR images are really high spatial resolution. They have a resolution of perhaps 40 or so meters. And so at the beginning of the animation, which is April 1st, 2017, there's an ice arch present in the northern part of Nares Strait. As you'll notice, none of this ice moves at all. South of this ice arch, it's still cold in this region. Ice is forming, thin ice is forming every day, and the winds that blow down Nares Strait will blow this ice southward. So I'll run this animation one more time. What you'll notice is that this arch remains rock stable for about a month, 6 weeks, and then essentially it suddenly collapses. So let me run this one more time. Hopefully, I can run it. Sorry, let me go forward now. So again, here you see, notice there's no motion at all here. These ice flows are remaining rock solid. We're now into May, and then suddenly there, the arch collapses. And once the arch collapses, then this multi-year ice can flux out of the Arctic. So this area north of Nares Strait is quite important because it's the region of the Arctic that has the oldest and the thickest ice. And so the ice in this region can be upwards of 4 meters thick now. And so the ice that leaves through Nares Strait is this really thick, really old ice. And this is the primary gateway by which really old ice leaves the Arctic. Thin ice leaves, a lot of the thin ice leaves the Arctic through Fram Strait, but Nares Strait is the region where most of the thick ice leaves. If you predict, jump forward 20 or 30 years from now, this is the region where the only remaining permanent or multi-year ice will be in this region. By the year 2060 or so, the rest of the Arctic in the summer will be ice-free. The only remaining ice during the summer, and that's ice that will persist from year to year, is in this region here. And this will then be an important refuge, if you like, for ice-dependent species once we lose the rest of the Arctic. In fact, the Canadian government has made a marine protected area in this region. The Inuktitut name is a place where ice never melts. And this was done essentially in recognition that we need to protect this area from all kinds of commercial activity so that it could be a refuge as time goes on. And of course, the concern is that if this ice is able to leave the Arctic through Nares Strait more rapidly than the past, this area may not last as long as we think it's going to last. So my group's been studying this for a number of years. We do a bunch of tools. I want to talk a little about synthetic aperture radar imagery. I want to acknowledge some of the students and postdocs who've been working on this, as well as my collaborators at Environment Canada, Polar Sciences Center at UW, and also the University of Alberta. So this is a picture of the ice flux through Nares Strait, a paper written about 10 years ago. And you can see that in the fall, there's lots of transport. Positive values are transport to the south. And then suddenly on January 4th this year, the transport went to 0. The arch formed, and this arch persisted through until the middle of July, where it collapsed and the transport started again. So this is a really remarkable cessation of this transport that these ice arches do. This is this ice arch from 2017. This is before the arch collapsed. You can see there essentially is only first year very thin ice in Nares Strait. This is after the arches collapsed. And what you can see is that now ice going way up into this last ice area is now starting to fracture because it's starting to now transport southwards through Nares Strait. So as soon as the arch collapses, one gets a really dramatic change in the structure of the ice to the north. It fractures quite quickly and starts to transport southwards down through Nares Strait. At the southern end of Nares Strait is this famous or very important Plenia called the Northwater Plenia. And it forms downstream of an ice arch. This is the ice arch that forms in the southern part of Nares Strait. And again, what this ice arch does is it stops the transport southwards. And as we'll see, there's very strong winds in this region. And so any ice that forms this region is quickly transported southwards, leaving this area of open water, which is known as the Northwater. I just want to show a couple of examples of how we can use synthetic aperture radar imagery and also ice motion vectors. So what we do is we take two consecutive SAR images, we compare those two SAR images, and we can essentially track ice motion by seeing how the ice flows, these individual characteristics change from image to image. So this is on May 8th, 2017, before the arch collapsed. You can see there's no ice motion at all. May 10th, the arch is starting to collapse. You can now start to see ice motion here. 2 days later, so this is really quickly for the climate system, suddenly you've got this huge flux of ice southwards. The arch is collapsing. And as the arch collapses, you can see that it's essentially the information, the arch's collapse is propagating northwards, and one is getting more and more motion in the system, fluxing large amounts of ice southwards through Nares Strait. This is a time series of the ice area flux. Again, we use those ice motion vectors to calculate the flux across that gate. And you can see that from 12th of May to about the 10th, sorry, 12th of April to about 10th of May, there's no motion at all. The arch collapses. And then you got this really large sustained transport, about 1,000 square kilometers per day of ice moving southwards through Nares Strait. We have essentially about a 4-year record now, and this is the daily ice motion across that flux gate. This is the arch that formed in 2017. You can see the remarkable reduction in the magnitude, but there was still motion. The arch collapsed, one had motion again. The arch formed again in 2018, again with some sort of motion to it. There was no arch in 2019. And in 2020, an arch formed. But if you compare this arch to these arches here, there was no motion at all. The arch was incredibly stable. The other thing you can see here is that actually there are instances when the transport is actually northwards. So negative ice area fluxes mean the transport is northwards. On average, it's southwards, but you can get events where you flux ice back into the last ice area from the Nares Strait region. So these are quite interesting. We don't really understand them. So lots of issues here, lots of complexity. What drives this different behavior? These are some of the sorts of things that we're trying to understand. I want to do one other example of ice motion. So this is 2019. In this year, an ice arch formed in the southern part of Smith Sound, Nares Strait. Here's the transport before the formation of the arch. The arch formed, and now again, there's no transport. No transport. Sometimes the ice motion algorithm picks up small ice moving southwards, and this is after the arch collapses. Again, one gets transport all through Nares Strait. But I want to focus on this area over here. So even in areas of active transport, this time here and this time here, there's no motion. This is the eastern part of Kane Basin. And as I'll show you in a minute, there's a reason why there's never any transport in this region here. All the transport is over on the western side of Smith Sound. So now I want to talk a little bit about some of the work that we do in trying to understand what's going on. So these ice arches are a function of the ice characteristics. Thinner ice is more mobile, also the atmospheric and the oceanic conditions. Nares Strait is a difficult place to study the atmospheric conditions. One reason is because it's so narrow. This is, if you like, is a cross section across Smith Sound here. This is what it looks like in a really high resolution digital elevation model. You can see that Smith Sound is about 50 kilometers wide. If you represent that in an atmospheric model with a resolution of 2.5 kilometers, you get a pretty good representation of the steepness of the boundaries and also the width of the domain. At 25 kilometers, which is a typical resolution that we have a lot of models are run at, you see that it's not representing, it just can't capture the steepness of the topography. It also can't capture, if you like, the width of the strait. So again, it is a challenge to represent the atmospheric flow in this region just because it's quite a narrow gap. And so the winds that blow down through Smith Sound do two things. They're responsible for the Plenia. They also represent a stress on the arches that form. And this is some work that we've been doing with this. There's a new 2.5 kilometer atmospheric model, which is available for about 20 years or so. And these are what extreme events look like in the region of Smith Sound. This is 25 meters per second. So the extreme wind events here have wind speeds of upwards of 25 meters per second. If you notice something, you'll notice that if you look in the vicinity of Smith Sound, The vectors, these are the vectors here, are, if you like, perpendicular to the pressure gradient. So the contours are the pressure field, whereas downstream, the vectors now are aligned with the contours of constant pressure. And this is an indication that the flow in Smith Sound is ageostrophic. That means it's not really strongly constrained by rotation. And then downstream, when the vectors become aligned with the pressure contours, the flow is geostrophic. And so this is essentially the geostrophic flow is essentially what Charney was trying to model with his first forecast. He would know he'd be able to study this ageostrophic flow in this region here. And then if you look into Smith Sound, Kane Basin here, you can see that there's this very strong wind speed gradient across. Winds are high on the western side. That's where the ice is being transported southwards. And they're quite low. And in fact, they're 0 meters per second on the eastern side. And that's because of this headland here, which acts as, if you like, as a barrier to the flow. So the winds are quite weak in the eastern part of Kane Basin because of the sheltering of this high topography to the north. And so that, if you like, explains this result here as to why you never see ice motion in eastern Kane Basin, and that's because the winds are really light in that region. So when you go to 2.5 kilometers, you can represent this wind speed nadir. If I showed you the same plot at 25 kilometers, you wouldn't see this. So it just shows you how important really high resolution is. I want to now talk a little about the ocean. And so this is the bathymetry of essentially Nares Strait. And this is a region here in Kane Basin where there's a sill. So the bathymetry is quite shallow in this region. And as we'll see, this has a really important impact on the ocean dynamics in this region. And this is work that I've been doing with Paul Myers at the University of Alberta. It's a very high resolution ocean model, a 12th of a degree, it's quite high resolution. And we have these 3 flux gates that I'll briefly talk about, one at the south, one at the north of Kane Basin, and one at the north of Nares Strait. So if you look at the heat transport across these 3 flux gates, what you can see is there are these events, again, where there's a strong northward transport of heat. They occur mostly at the south, but you also see them at the middle and the north gate. Most of the time they're synchronous. So if you get a strong transport at the south, you also see it at the middle and also at the north. But if you look at these things, there's another more fundamental thing happening. The heat transport is increasing over time at the south, but not at the middle or the north. And so this means, if you like, that heat must be accumulating south of the sill. And if you look at this is the heat content in the ocean, both north and south of the sill, you can see this steady increase in heat. So the southern part of Nares Strait is becoming warmer and warmer, where that heat is not really being transported as of yet northwards. And so that is essentially consistent with this. And now what I want to do is I just want to finish up by looking at one of these events here, where there's a strong flux of heat northwards. So this is a cross section. This is the south of Nares Strait. This is the north. The shading is the temperature. The contours are the salinity. And what you can see is this is the sill here. And so for most of this year, there's a really profound impact. The sill, if you like, prevents this warm, salty Atlantic water from penetrating farther north. So there's this really dramatic change across Nares Strait with the presence of warm and salty Atlantic water to the south. Essentially, you don't see any of that water to the north. At the surface, there's, of course, cold and fresh Arctic water. And I'll run the simulation one more time. And what you'll see, if you look at the time here, is that in December, there's an event happens where this heat is fluxed over the sill. It gets over the sill north into the northern part of the basin. So let me just, I'll get back up and run this one more time. So here we go. You see for the early part of the year, this heat can't get over the sill. This is because, again, rotational constraints limit the transport northwards. And then starting around the 1st of December, the heat transports northwards. So this is the before and after picture. This is the start of the year in May. This is the end of the year. And you can see that at the end of the year, this heat had been able to get northwards. And so we think that once this heat gets over the sill, it's now available for melting sea ice and things like that. You'll notice the heat is always below. This is a kind of an interesting thing, is that this is where very warm water is also very, very salty water. And so the presence of the salt means that this water is more dense than the surface waters. And so this Atlantic water is always about 300 meters down throughout the whole Arctic basin. But again, you can have instances where one can bring this water up to the surface where it's available to melt. So I just want to finish up by talking about climate change and the impact that arches have. This is the thickness of sea ice north of Nares Strait. You can see that the ice is getting thinner by about half a meter per decade. So again, our record starts in the 1980s. And so you've gone from 5-meter thick ice to ice that's about 3 meters thick. So this really profound change in the thickness of the ice. If you look at the transport down through Nares Strait, this is an earlier paper by Ron Kwok, which had about 10 years worth of ice area flux data. We have about 3 years of data, but you can see this dramatic increase in the transport. In fact, the mean, if you like, in this later period is larger than the largest transport we had in the earlier period. So again, the Arctic is changing. As the ice gets thinner, it's easier to move ice down through Nares Strait, and there's this increase in ice area flux. The other thing that's happening is if you look at the duration of the arches, how long they last, this is a time series, and you can see that back in 1995, the arches lasted for perhaps 200, maybe 250 years. Now they're lasting about 100 days. Now they're lasting about 200 days, now they're lasting about 100 days. So these arches are becoming less stable, less duration, and that's one reason why we think there's more transport. If the arches aren't there for as long, there's just more time for ice to flux southward. So this, again, is a very profound change that's happening. So just to conclude, again, so the Nobel Prize this year was awarded to scientists who study complex systems. Of course, takes a village to win a Nobel Prize. So Manabe's award was really rooted in von Neumann's interest in numerical weather prediction. He thought this was the most complex, interactive, and highly nonlinear problem that had ever been conceived of. The geophysical fluid dynamics laboratory, which spun out of von Neumann's interest, provided an environment where Manabe could make these really foundational contributions. And of course, it was a fantastic learning environment. It was I often think it was like learning climate science by drinking, water from a fire hose. Every week, a leading scientist was in the laboratory talking about their work. Manabe was incredibly interested in the lowly work that the graduate students were doing, and it was just an incredibly fascinating learning environment. So he provided the first realistic estimate of this climate sensitivity parameter. Modern climate models, which are orders of magnitude more complicated, essentially give the same result. Of course, they give us much more detail, but the basic idea of how CO2 impacts climate was actually solved 50, 60 years ago. In fact, Manabe, when I've talked to him over the years, he always stressed that as, kind of academics, we should be focusing on really simple first order solutions to problems. Let other people work on the engineering aspects of getting essentially all the processes right. But really, and this actually has been quite influential in my own research. So I, again, look at these ice arches, which are really, really interesting. They appear to be weakening, probably as a result of thinning ice and also a warming planet. And again, their weakening is going to hasten loss of Arctic sea ice, especially this multi-year ice, which is the ice that should last the longest. And it's one of these catastrophic impacts that we talked about in the IPCC reports that will occur if we continue to warm the Earth. So thank you very much. This is an image of one of these northern ice arches. They're just so beautiful things to look at. This essentially is thick multi-year ice, probably 3 meters thick. This is very thin ice, which is forming just because it's so cold. And just this contrast between the thick multi-year ice and the very thin ice that's forming, I think is just really beautiful. So thank you, and I'm happy to answer any questions that people have.